Hello all, welcome to this presentation of a case study involving premature corrosion of stainless steel tubes by acetic acid in an ester plant. Uh, you will notice at the end, this is a design-induced corrosion problem. It happened quite unexpectedly. Mm. This slide shows the flow sheet of the flow sheet uh, of a particular heat exchanger in the ester plant. The plant produces acetic acid based ester. So what you see on the left side is a shell and tube heat exchanger in which the the reactor gas after the reactor gas after the reactor comes in with, with a high temperature 131 degrees centigrade gets cooled down to 115 degrees centigrade. This heat has gone to the input gas, that is on the shell side. The input gas on the shell side, the gas comes in around the room temperature, little bit above room temperature 70 degrees, and gets heated up to 85 degrees. So the difference is the tube side hot gas enters at a higher temperature, gets cooled to lower temperature, whereas the shell side, that is the raw material gas, enters around 70 degree and gets heated up to 85 degrees centigrade. So unfortunately, the corrosion problem has occurred in spite of the tubes are made of very good stainless steel 316L, which is a very common grade, very much used in chemical plants. So this is the position of the leaky tubes as seen from the cold end. By cold end, I mean the right hand side of the earlier diagram where the cool gas comes in. That is called the cold end. And this, in any investigation like this, the position of the leaky tubes is very important. You can see here the leaky tubes is not random. The leaky tubes the leaky tubes are here. The most of the leaky tubes are here only, except one or two isolated tubes here and there. This means there is some problem in the temperature region, in the temperature profile on this left hand side. This is a cross section of the number of tubes. So what you see is it's a horizontal it's a horizontal tubes but vertical cross section. So we should be able to explain why this preference on this left hand side. You will see later this is some kind of a design induced effect. So what you see here, the particular location where the particular location at the end, the tubes are very long. This is the end of the tubes, and what you see here in this cross section, the previous slide, in this cross section you have seen the tubes, but here is on the longitudinal side. On the longitudinal side, this is the longitudinal direction, and that particular location what you see, whereas the tubes are somewhere on the bottom and also left hand side when you look from here. So there is a preferential location for the leaky area. This we will see little later, and this preferential location is very close to the gas input gas inside before it gets and then the cooled gas is almost coming out. The almost it is quite cooled coming from the reactor upstream. Uh, this is the leaky spots. You can see the outside of the tubes is quite clean. Clean means not generally affected except the leaky hole. You can see the leaky hole on two tubes, adjacent tubes. This is one tube, this is another tube. Adjacent tubes, you can see the leaky hole. Whereas if you see from the inside where the gas comes in after the reactor. You'll see the composition of the gas a little later, but you can say general attack, some kind of an acidic attack plus a leaky hole. So this shows. So what we derive from this picture is the inside is corrosive, the inside atmosphere has become corrosive, whereas the outside is not corrosive except the leaky spot. The leaky spot is started from the inside and ending from the outside, resulting in leaks. Hmm. So this is the detailed microstructure of the inside surface, because we have seen the leaks have started from the inside and then going towards the outside. So we concentrated on looking at the microstructure on the inside surface. The inside surface, you can see here, it is this is called sensitized microstructure. It is not a normal 316L stainless steel structure, and that is called step structure. This is not a step structure. This is a sensitized, means the grain boundaries are revealed. The grain boundaries have become popular and corrosion attacks on the grain boundary. Whereas here on the same tube, little away from the leaked spot, just to show the general microstructure of the tube itself, here also you can see to a certain thickness from the inside surface, you can see the intergranular nature. So this shows that the tubes are sensitized during manufacture, and since sensitized microstructure leads to intergranular corrosion. That is what we are seeing here. The grain boundaries are become sensitized. Grain, intergranular. That means the grain boundary leaks, gets leaked. Intergranular. Inter means between two grains. So that is intergranular corrosion. Uh, so this is now we also looked at the corrosion far away from the leaked area, just to make sure what is the quality of the tubes. And you can see here the corroded end, and this is the microstructure on the inside surface near the hotter uncorroded end. Uncorroded end. Here also you can see the structure at the surface is quite different from the structure from the inside surface. This is the inside surface, this is the inside the tube, and this is the surface structure. And surface structure again shows a different structure. That means the tubes got sensitized. The tubes got affected during manufacture, and this is called intergranular sensitization, leading to intergranular corrosion. Mm. So here is a typical fluid composition. So something, the pure ester is not corrosive, and the acetic acid is corrosive provided it is in the liquid form. Here you can see the reactor, the tube side reactor coming from the reactor. Already it has got so much of acetic acid, whereas the cycle gas which is getting inside for reaction purposes has got only very little trace of acetic acid. So this acetic acid is a corrosive corrosion acid. And you can see here correspondingly, corrosion does not take place if there is no moisture. The acid has to be dissolved in some moisture. You can see on the tube side, sufficient quantity of moisture is there, which is not expected. Whereas here you can see the input gas, only the trace of moisture. So what is happening here? The moisture content is increasing. That is where the design purpose, we will come to the design point. So these are the two most important, the acid with moisture at a certain temperature. See, the temperature is, we'll see later, little as you have seen in the second slide, the operating conditions. Yeah, here is the operating conditions. The tube side, that is where the reactor gas comes in. You can see at three different locations. It comes in at a little higher temperature and gets cooled to a lower temperature. And the shell side, the recycled gas gets heated up from 70 to 85 degrees centigrade. So the operating conditions, these are all operating conditions, but actual conditions are different. And the actual conditions, we saw the temperature increasing. The actual conditions are temperature is less than the dew point. So once the temperature is less than the dew point, like this 120 and 130, which is a border line, but it is less than dew point. At that location, corrosion occurs, because the dew point is the place where acid vaporizes. In the vapor, it is not corrosive. When the temperature goes down, it becomes liquid, and the liquid is corrosive. So the diagnosis: originally the tubes are defective. The carbon pickup, that is leading to intergranular corrosion, and that carbon pickup happens during manufacture. So it is a quality issue. So because of carbon pickup, the tube structure has become sensitized. That means sensitization means it becomes susceptible to localized corrosion, in this case intergranular corrosion. So that is what has occurred by the condensate acid. Condensate acid, it is not a vapor. The vapor is already condensed to liquid form. So the condensed acid is corrosive, not vapor. That is why the corrosion has occurred only at particular location where the temperature has already come down. When the input from the reactor, when the temperature is high, corrosion does not take place at that location. When the temperature comes down and the material is defective, intergranular corrosion has taken place, and that leads to the leaking on the corroded areas. Now, remedy: avoid carbon pickup during manufacturing. So avoid carbon pickup. This due to certain operating procedure, when the tubes are made, they are heat treated. During heat treatment, carbon can be picked up. So carbon pickup should be avoided during manufacturing. Ensure thorough insulation of the shell. In this case, what has happened at that particular location, at the end portion of the heat exchanger, we saw some oval mark, and where the tubes are started leaking, and the whole thing, the whole exchanger is insulated. Insulated means the heat must be conserved. Whereas on that particular location, on the shell side, the insulation was not done, because the whole exchanger is under support. The supports were not insulated, so the support took away the heat, and so leading to condensation, and that condensation has resulted in corrosion. So thank you very much. So the remedial measure mm, is to make sure condensation does not take place. Thank you again.